Binary conversion. From decimal to binary, and back again. A very poor imitation of the Hobbit's title. But seriously, we do need to talk about binary conversions and how we go from decimal to the binary and from binary to decimal, and why does it matter? All right, so let's jump straight into this. First of all, let's talk about number-based systems and start off with base 10 and converting base 10 to base 10, since we use base 10 number systems all the time. We understand them fairly intuitively. So when we're thinking of base systems, each digit of a number represents the base to a power, starting with 0 for the digit on the right. Now, whenever you're dealing with a base, the actual digits are always going to be 0 to 1 less than the base. So in a base 10 system, or the usual number system that we use, our digits are 0 to 9. You can never write 10 as a singular digit. 10 is always 2 digits. So keep that in mind as we move forward. You start, like I said, with 10 to the 0, or the rightmost or smallest digit. For each digit you move to the left, you increase the power by 1. So for example, if you have a 3-digit number, the leftmost or first digit, how you want to say it, would be 10 to the second, the middle digit would be 10 to the first, and the rightmost digit would be 10 to the 0. Given a slightly less abstract example, take a look at the number 123. If I wanted to convert 123 from base 10 to base 10, I would do it as 1 times 10 to the second, plus 2 times 10 to the first, plus 3 times 10 to the 0, or 100 plus 20 plus 3, or 123. We can continue this pattern for as long as we want, and just sort of another way of representing it. Here we've got the rightmost digit, that's 10 to the 0th power, in other words, representing ones, because 10 to the 0 is 1. The next digit, the 2, is 10 to the first, or the tens place. Next digit over, this 1 here, is 10 to the second, or the hundreds place, and so on, so forth. If I needed a number that was in the thousands, so I had an extra digit here, that would be 10 to the third, or the thousandth place. So it works pretty well. It's a pretty simple system once you back away from the scary sounding math words and realize, oh yeah, this works out. This checks out. This is how we usually use our math. So when we start talking about base 2, it works the same way. It's base 2, so our valid digits are 0 and 1. You can never, ever write a 2 in base 2, just like you can never write a 10 as a single digit in base 10. Which leads us to one of my favoritist sayings. There are exactly 10 types of people in this world. Those that understand binary, and those that don't. So how exactly does that statement work, right? So let's look at 10 as a binary number. Again, binary, base 2, has 2 values per digit, 0 or 1. So if we start with the rightmost digit, that value is going to be 2 to the 0 power, with the power increasing by 1 for every digit to the left. That means if I want to convert 10 binary to decimal, that would be 1 times 2 to the first, plus 0 times 2 to the 0, or 2 plus 0, which equals 2. So 10 in binary is 2 in decimal. Thus, my saying works. Okay, so very clever, Professor. Have a golf clap. But, okay, practically speaking, why do we care? Why does this matter? Well, as programmers, we care because at their core, computers are sequences of zeros and ones. Everything in a computer at some point can be reduced to a sequence of on or off, 0 or 1. Every aspect of computing is touched by this. Let's look at RAM as an example. So RAM, random access memory, that's the stuff that, when you turn your computer on, you got to load stuff in. You need to have at least 8 gigabytes of it these days because Windows just keeps getting bigger and bigger and bigger. Not uncommon for computers to have more than 8 gigabytes of RAM. My machine has 32 gigabytes. I'm a little bit of a oddball case because I do video processing and other high RAM applications that most people don't do. But there's people out there with 64 gigabytes of RAM and more in their machine. So yeah, lots of RAM. RAM for everybody. So keep in mind, go over some of our numbers here. A byte is 8 bits. That is the smallest possible unit of memory in a computer. A giga is a number with 9 zeros. So 8 gigabytes is an 8 followed by 9 zeros, or colloquially known as 8 billion bytes. Now, it wasn't that long ago that it was literally impossible for a computer to have more than 4 gigabytes of memory. Every byte in a stick of RAM is a physical location. It might blow your mind a little bit to think of it that way, but that's what it is. Every single byte on that RAM stick is a physical location. The computer needs to be able to address or find that physical location. And it does that by assigning a unique integer ID to every physical location in memory. So what happens if you have a 32-bit operating system running on a 32-bit CPU? So, it used to be that we had 32-bit CPUs. The CPUs could only process 32 bits at a time. They literally could not process more in a single operation. So what is the maximum sized number you can have with 32 bits? Well, 2 to the 32nd is 4,294,967,296, which basically means that a 32-bit operating system can refer to no more than 4 billion and some change physical locations. Or to put it more commonly, you can have up to 4 gigabytes of RAM. That's why on a 32-bit operating system, you can't have more. You also couldn't have hard drives larger than 4 gigabytes. Hard drives did exist that were larger than 4 gigabytes back in the 32-bit era, but you had to split that up into different logical drives. So you still had one physical drive, but as far as the computer was concerned, you had to assign it as 2 drives or more. As a quick side note, you can't hit the limit on memory on 64-bit operating systems. You see the number on screen. I don't know how to read that number. I just don't. But I did do some quick, back of the napkin, napkin math calculations, and that's, over 100 million sticks of RAM. So, yeah, you're not reaching that number anytime soon. So there's one reason why we care about binary. Let's go over a little bit more fun reason why we care about binary. In the game Civilization, I'm talking specifically Civ 1 is where this bug was found. And is still found, I believe. I don't think it's ever been patched. Gandhi could go warlord mode. I mean, he would suddenly go from the most peaceful individual that we all know him from history as to scorched earth, nuke everyone. I am not joking. It was like a switch suddenly got flipped in his head and he was done with everyone. So what happened? Well, if you have a byte, 8 bits, and every bit is turned on, so you have 8 ones. Well, there's 2 ways that can be represented. That can either mean -1 when the number is signed. In other words, you want to be able to represent negative numbers, or 255 if it's an unsigned number. So if you have 0 in decimal and you subtract 1, well, you get -1, or bits 111111111. I think I might have said too many ones there. But now what if that number isn't signed? 8 ones, binary has the value of 255, or the highest possible aggression value. Quick side note, if you do any sort of classic gaming or DOS gaming, you will notice the number 255 pop up a lot. And that's because that is the maximum integer unsigned value that can be stored in a single byte of memory. And most old games, if they're going to store a number, they're not giving it more than a byte of memory. You can also see this kind of effect happening in, say, Skyrim. If you do an enchant loop over and over again, the value of an enchanted item goes up to 2 billion and change, and then all of a sudden becomes massively negative and usually crashes the game. It's because you overflowed the bits and the number went from being positive to negative. So yeah, that's why we care about wanting to be able to do this math and knowing what binary values equal decimal values and vice versa. So a quick summary on the binary to decimal, because that part's pretty easy. Each digit is a base to a power, starting with 0 on the right-hand side. Multiply the base to a power by the value of the digit, and you add everything together. For example, if we have the binary number 1010 or 1010, we calculate that out to be 1 times 2 to the third, 0 times 2 to the second, 1 times 2 to the first, and 0 times 2 to the 0. Or we get 8 plus 2, or 10. So 10 in decimal is 1010 in binary. But what if we want to go the other way? What if we want to go from decimal to binary? Well, that's a little more interesting. We got my glorious handwriting here on the side. So the general idea here is that you take the binary number, divide it by 2. You write the quotient down, write the remainder off to the side. That quotient becomes the new dividend, and you repeat the process until the new dividend becomes 0. And you typically do it with drawing an upside down division symbol. So if I'm going to convert 10 to binary, I'm going to write 10, my upside down division symbol. 2 goes into 10 5 times with a remainder of 0. So I write down the 5, 0 off to the side. 2 goes into 5 2 times with a remainder of 1. So I write down the 2, 1 off to the side, upside down division symbol. 2 goes into 2 1 times with a remainder of 0. Upside down division box. 2 goes into 1 0 times with a remainder of 1. I now have a 0 here, so I stop. I do not continue. And then I write the number with the bottommost number being the leftmost number. So this is 1 0 1 0. Write down 1 0 1 0, or 10, which, as we just saw on the previous slide, is what we need. Let's do a couple more problems like this, because this isn't quite as obvious as going the other way, going from binary to decimal. So let me switch around equipment here. Nope, that is the wrong tool. All right, so let's do a simple one. Let's do 72. So upside down symbol. All right, so first round here, we have 36, remainder of 0. Do it again. 18, remainder of 0. Do it again. We have a 9, remainder of 0. Hey, we're finally getting some remainders now. So 2 is going to go into 9 4 times, remainder of 1. 2 with the remainder of 0. You don't have to write the 2's there. I sometimes do that. Most of the time I don't. 2 goes into 2 one time, remainder of 0. And 0 times with the 1. So I have 1, 0, 0, 1, 0, 0, 0 for my binary number. I can double check that. Remember, power-wise, this is 0, 1, 2, 3, 4, 5, 6. So I could easily check this by doing 2 to the 6th plus 2 to the 3rd, because everything else is zeros, and of course we've got 1s there. So it's just 2 to the 6th plus 2 to the 3rd. Pop up the calculator here real quick. 2 to the 6th plus 2 to the 3rd. 72. Excellent. That is what we wanted. Move that off the side there. So everything works. A good sort of like check to make sure that you've got at least a somewhat sane answer. If you have an even decimal value, then this should be 0. If it's odd, then it should be 1. So let's take a look at a larger problem. Let's do one more round of this. Do a ghetto reset here. Okay. And by the way, I'm not this good with the mouse. I have a drawing pad that I am using to do this writing with. I am not this good with a mouse. All right, so let's look at the number 221. That should have most bits turned on because that's pretty close to the max of 255. So 221. So that is going to be 110 with a remainder of 1, which is exactly what I would expect. That's going to be 5, 5 with a remainder of 0. And 2 going into that is going to be 2, 7 with a remainder of 1. That's going to be 1, 3 with a remainder of 1. That is going to be 6 with a remainder of 1. That is going to be 3 with a remainder of 0. That is going to be 1 with a remainder of 1. That's going to be 0 with a remainder of 1. I've hit 0, so I stop now. And then to write this number out, it is 1, 1, 0, 1, 1, 1, 0, 1. Now again, I can check this. Powers, remember? So this would be 2 to the 7th plus 2 to the 6th. We don't have a 5. Plus 2 to the 4 plus 2 to the 3 plus 2 to the 2. We don't have a 1. Plus 2 to the 0, which is going to give us our odd value here. And now I can switch over to the calculator and verify that this is going to work. So I have 2 to the, not 2 to the 6th, I have 2 to the 7th, plus 2 to the 6th, plus 2 to the 4th, plus 2 to the 3rd, plus 2 to the 2nd, plus 1, 2 to the 0. 221. That is the number that I expect. Again, it's not hard. You just have to take your time and be very careful with how you write things, because the most probable source of mistake is going to be not keeping your numbers lined up correctly and getting those off sync and being short a digit or maybe possibly introducing an extra digit. That would be the main danger with this. So just take your time, be careful with how you write down the numbers, and you should be good. Remember to go do the homework that's on Canvas, just a small selection of problems for you to do. And we'll be back at it next week, taking a look at algorithms.